I, I hope you can all hear me. I'm chairing the this second MQ session, and we have Jamie waiting to present on what's new in MQ. So without further ado, I shall hand over.
Okay. Right, thank you, Mel. So I'm Jamie Squibb. I'm one of the development leads for MQ in the Hersey lab in the UK. And so in this session, we're going to discuss what's new in MQ, primarily over the last couple of years since the 9.1 long-term support release. So we'll kind of go through that. But first, it's just worth having a look at what the MQ is all about, and just providing an overview of some trends we're seeing in the industry. So firstly, MQ is the de facto standard for enterprise messaging, used by many of the largest customers and companies around the world. The figures kind of stand for themselves. MQ is a way of easily connecting applications together so they can exchange information. It scales to billions of messages a day for some customers, whilst providing that reliable connectivity between a wide range of environments and platforms in a secure way. So there are four main industry trends that we are kind of seeing kind of appearing and have been around for for a while now. So the first one is around developer agility. So increasingly application teams or developers are being empowered by their organizations to be more autonomous. They want to be able to complete their own tasks without depending on other teams providing services for them in a way that they have to wait for those services to be completed or those actions to be done for them. So it's important that they are able to kind of react fast and quickly to kind of like industry trends and market needs based on what they perceive and need to happen. At the same time, those teams are being empowered to choose where they deploy the tools and services that they use, which means that we're seeing increasingly systems being deployed in a wide range of clouds, and many customers and companies have more than one environment where those services are being hosted, and they need those services to connect together from wherever they're running. Thirdly, we're seeing that the traditional teams that look after the infrastructure are being challenged to do more with less to drive cost savings in the organization. And so they're being tasked with simplifying their management of those systems and automating many of the actions that they may have traditionally done manually. And then finally, we're seeing lots of organic growth in organizations to respond to different workload patterns and different market trends. So environments which have been traditionally been built up over many years are now being expanded and extended for additional scalability, availability, and security. So how can MQ actually help you satisfy these sorts of trends? So there are kind of some main items here, and many of the features that we're going to discuss throughout this session fall into some of these categories anyway. For developer agility, it's easy to build self-service pipelines for your developer application teams using continuous integration or continuous delivery to actually allow them to provision their own environments for MQ and deliver updates to those environments without needing manual actions to be performed by infrastructure groups. MQ has been built to connect applications across data centers for many, many years, and it's been proven at doing that. So it's actually also a natural fit for connecting applications that span multi-cloud environments. The fast, secure, and reliable connectivity it provides is ideal for allowing those applications to communicate in the different environments where they may be running. In terms of operational agility, MQ queue managers are well suited for running in containers, which are increasingly popular for operational deployments. They allow you to build a pattern of deployment that you can repeatedly deploy one after the other for scale to spin up and down environments based on need. And then finally, for organic growth, in terms of adding that scale and availability, MQ has numerous capabilities that underpin these features that you can exploit. But increasingly, we're seeing the need for applications to be deployed in an active model rather than an active passive model instead. So by active passive, it's where you've got one instance of a queue manager or an application running with a kind of like a standby ready to take over should that fail. But increasingly, to support the scale and availability of cloud deployments, it's increasingly important to think about how you can have multiple applications serving application instances serving the need for that application, and have those applications be able to connect to one of a number of queue managers for 100% availability and as best as achievable. So if we just now look at what MQ's been doing with its delivery model for the last couple of years. So, well, since 2016, we've had a dual support environment where we have a long-term support release, which is made available approximately every 2 years. And those releases, when they're available, have the traditional 5+3 years support available for them. And they have maintenance fixes provided during their life. But new features only arrive in those long-term support releases when those releases are originally made to market. To allow for a different need and allow features to be taken advantage of sooner than waiting for 2 years, we also have a continuous delivery offering, which is made available approximately every 4 months or so. Each continuous delivery release builds upon the latest long-term support release in the market, and it adds additional function and features in addition to any fixes that we've identified. This allows you to take those continuous delivery releases and either prototype those features so you can exploit them as soon as they're available in long-term support, or you can deploy those continuous delivery releases into your production environments and exploit those new features as soon as they're available to allow you to be more agile and adopt these features as fast as possible. You can mix and match these releases so that you've got connectivity between them in the same way that you would do for any traditional MQ release. So in this presentation, we're going to discuss the features that have been delivered since 9.1 long-term support release. So this is going to be a roll-up of those features that we've delivered throughout the 9.1 XCD release cycles, all the way up to the 9.2 long-term support release that was made available earlier this year. So this slide is a bit of an eye test. You do not need to look at all of the tiles. We're going to cover most of the main points throughout the session, but it just gives you an overview of the amount of features and enhancements that we're making to MQ and that we've made over the last couple of years. So let's just look at where MQ needs to run. So MQ, as I'm sure you are aware, is designed to run in many different environments, both on-premise and in the cloud. So it continues to be available on all of the different environments that you're used to in your data centers, ranging from Unix, Linux, and Windows to the MQ appliance and the ZOS mainframe. Sorry. In addition to that, MQ is also available and suited to run in cloud environments, available as a managed service that IBM provides hosted in IBM Cloud and AWS, or you can run it yourself using your own containers in any of the cloud environments that are available. Also, since the acquisition of Red Hat within IBM, the OpenShift platform has become increasingly prevalent, and so MQ is well suited to running in that environment too, based on the OpenShift container platform. So if we look at MQ and containers in a bit more detail, MQ is actually well suited for containers because MQ is designed to be lightweight and run at any size, so it can scale down to any container deployment that you need. IBM itself deploys containers running in small scale at large volumes for customers. when you deploy MQ in containers, queue managing containers, then they're more likely to be application centric rather than large queue manager deployments that support multiple applications or multiple tenants. So think about when you do this of actually deploying a larger number of smaller queue managers based on a template that allow you to support different applications. When you manage those applications, container environments and orchestration tools such as Kubernetes allow you to manage very large numbers of these containers and automate the deployments of them and their monitoring. So it allows you to actually build large dynamic deployments of MQ that allow you to actually support the applications that you're running for your business. At the same time, MQ can be supported in high availability environments within containers. You can use the built-in capabilities of the orchestration layers such as Kubernetes to monitor those containers and restart them should they encounter a problem. But you can also take advantage of some of the MQ capabilities that provide and build upon those for even higher availability. And we'll see some of that throughout the session. MQ is also available as part of the IBM Cloud Pack for integration. So this is a suite of integration products that are bundled together in a single offering based on the Red Hat OpenShift platform. It allows you to actually build your integration solutions in a single unified way without having to deploy and manage each component of your infrastructure suite separately. IBM is committed to building and increasing the value of this offering over time and on the OpenShift platform, but it's built upon the MQ running in containers and built on the certified container that is fully supported for production use. It includes built-in capabilities for logging and monitoring of your infrastructure within the Cloud Pack, and it's very flexible in allowing you to actually mix and match what you use, how you use the resources available within the Cloud Pack, and how you adopt it over time from your traditional systems. There's actually a specific session that discusses MQing containers in Cloud Packs by one of my colleagues, Matt Lemming. That's session 5AU. So if you want to know more about how MQ runs in containers or the Cloud Pack for integration, that's a good session to go and listen to. So now let's look at all the different features that MQ has been adding over the last couple of years. Grouped by theme, so we'll start off with some fault tolerance enhancements to allow to see how you can actually improve the availability and resiliency of your data. So MQ has a number of high availability features that have been around for many years. On ZOS, we have queue sharing groups, which are the premier solution for high availability because you have access to messages from any of the queue managers in a group because those messages can be stored in the Sysplex coupling facility for ZOS. On the distributed platforms, you have multi-instance queue managers and HA clusters, which use an active-passive model with some shared storage. This means that you can have an active instance of your queue manager running that has exclusive locks on that shared storage. And if that active instance fails and releases the locks on the storage subsystem, then those the passive instance can acquire that lock and restart and take over the service for you. This means that you can build highly available systems, but they do depend on the shared storage and the management of that. Some customers provided feedback that they found it difficult to manage that shared storage, especially if they were trying to implement connectivity and high availability across data centers, because the shared storage had to be available to both locations and connectivity to it. So we then added a different style of high availability into the MQ Appliance when that was introduced into the market in 2015. The MQ Appliance is an hardware offering provided by IBM, which is available to run and host your MQ queue managers for you. It only runs MQ, you cannot run anything else on it. So all applications connect to the Appliance queue managers remotely. But the high availability solution we built into the Appliance is one based on replication. So rather than needing shared storage, you can have a pair of appliances that replicate data synchronously between them, so that in the event of a failure of one of the systems, such as a power outage or something else like that, the second appliance can automatically take over and start the queue managers for you. The appliances provide heartbeats between them, so they can automatically take over in the event of an outage without any operator intervention. This was actually very popular as a very attractive model for people because they had struggled with shared storage, but not everybody wants to deploy a hardware offering in which to gain this sort of capability. So we then added an equivalent feature to MQ on Linux called Replicated Data Queue Managers, which is available on Red Hat Linux. In an RDQM solution, which we call it for short, you have 3 standard Linux nodes or Linux systems, which have just standard Red Hat Linux installed. They have local storage only, so you do not need any shared storage components in your infrastructure. And you can configure those 3 systems together in a group. The group then has some management software associated with it that allow those nodes to heartbeat each other and monitor the system. And then we have some disk replication technology that we use that allows data written to one of the nodes to be synchronously written to the other nodes in the group. Those two features are provided and built in by the RDQM offering using some packages that MQ then reuses and implements to achieve that result. MQ, you can then have a queue manager created that you run on one of the nodes, and that queue manager is actively writing data to the local storage on that node, with the data being synchronously replicated to the other 2 nodes in the group. Should the node fail, or the queue manager can be automatically started on one of the other nodes in the group, and the data is available to that queue manager on those alternative nodes because of the synchronous replication. Should one of the nodes, that node that failed then come back, the data is then automatically caught up on that node, and then that node can then continue to take host queue managers and be a failover for one of the other nodes should they encounter a problem. On top of this, each queue manager can have its own dedicated IP address that's independent from that of the nodes on which it's running. This means that when queue managers move between nodes, either in response to an outage or for maintenance, the application can connect to the same IP address and access that queue manager on whichever node it's running. So the IP address moves with the queue manager as it moves between the nodes. You can actually then have multiple queue managers in this environment, so you can make best use of the resources of those nodes, with each queue manager moving independently between the nodes. This provides a kind of a great framework for having high availability for both individual queue managers and groups of queue managers that support an active-active workload for applications. That was released in 9.1 long-term support release. More recently in 9.1.5, we've actually extended this to provide both HA and DR as a combined solution. In the 9.1 release, you had the 3-node solution I showed on the previous slide, which was synchronous replication and automatic failover of queue managers between the nodes. But you also had an alternative option of a 2-node solution with a manual failover between those nodes that's more geared up for disaster recovery. However, it's increasingly common that you want to have both features available to you in your solution. So in 9.1.5, you can actually have disaster recovery built on top of an HA group. So in this environment, you have 2 HA groups, one in one site and one in another site. Within each of the HA groups, you have the high availability feature that I discussed before with automatic failover and synchronous replication. And at the same time, you can have the data being asynchronously replicated to a second group available at a remote location. So here in this slide, we have a queue manager running on node 1. The data for that queue manager is being synchronously written to nodes 2 and 3, so that if the queue manager fails over between those nodes, then it has access to the same data. But at the same time, the queue manager's data is being asynchronously written to the nodes 4, 5, and 6 at the remote location. So this means that should the entirety of that first HA group fail because of a site outage, the queue manager can be started at the other location, and you've got an equivalent high availability capability at that location too. You can actually have queue managers running in both HA groups simultaneously, with each of the groups being a redundant disaster recovery option for the other group in the other location. So here I've got queue managers running in nodes 1, 2, and 3 that can fail over to nodes 4, 5, and 6. And similarly, I can have queue managers running on 4, 5, and 6 that can fail over to the group at the top. This provides a really flexible solution, allowing you to have an active-active model with queue managers running in both locations, whilst having the redundancy built in that allows you to fail them over to the other location in the event of an outage. If we now look at containers, I mentioned that you can have MQ has high availability built into both itself that can be built on top of the high availability options that Kubernetes provides. So Kubernetes will automatically monitor queue managers running in a container in the pods on the nodes that it's managing. And if that queue manager fails, or the container fails, I should say, then the Kubernetes will automatically restart it. But Kubernetes is very defensive in how it does that, especially for stateful containers such as MQ. So to avoid the situation where Kubernetes will not restart the container because it doesn't know if it's actually running on a node that it's lost connectivity to, you can actually use a multi-instance queue manager solution at the same time to provide you with increased availability for your queue managers. In this scenario, we have a stateful set of 2 replicas. So we have an active instance and a standby instance. And then we use the highly available container storage as the framework for the multi-instance queue manager. So we can start both those containers. The first instance that acquires a lock on the storage becomes the active instance, and the second instance sits there waiting to take over should the active container fail. This actually works really well and is the kind of like the recommended best practice for MQHA in Kubernetes, which you can actually manage using the MQ operator in OpenShift for improved usability. In both of those solutions that I discussed, queue managers have to restart when they move between nodes or containers. So to support improved restart times, we've done quite a lot of work inside the queue manager to speed up the time it takes for that queue manager startup processing to complete, both for managed failovers where you instigate them yourself in response to planned maintenance, or for abrupt failovers in response to a failure. So in this chart, you can see that we've improved the startup time for both these scenarios for multi-instance queue managers and for RDQM. So you can actually now have a busy queue manager restart in a small number of seconds or even sub-second for particular environments. So this actually allows you to get your queue manager back up and running to support your business with minimal downtime. On ZOS, one of the features that we added in 9.1.2 is for support for Z Hyperbytes. So Z Hyperbytes is a feature of the ZOS platform that allows you to extend Metro Mirror to replicate your data to a second location. So with Metro Mirror, data is written first to the primary location, and then it is then sequentially written to the second location for availability reasons, such as a disaster recovery backup. This does mean that there is a performance impact of enabling Metro Mirror because you're writing data to one location and then sequentially writing it to a second location. So that can impact performance for busy systems. So to improve that, Z Hyperbytes allows the data to be written in parallel to both locations. So this actually mitigates the sequential performance impact that you would have of enabling Metro Mirror. So MQ now supports this for its active log datasets. So you can configure Z Hyperbyte to do this for improve performance of your queue manager recovery logs. Okay, so having looked at some of the resiliency enhancements, let's now look at how we can build solutions that are active-active rather than active-passive as well. So by active-active, we mean that applications can connect to one of a number of queue managers to support the business function they're trying to achieve. This is because however resilient you make an individual queue manager, there will always be the potential for that queue manager to be unavailable, even for a short period of time during a failover. And you also can achieve better scale and resiliency by having multiple services that an application can use. So here we have multiple instances of an application and multiple queue managers that those applications can connect to. And we have to then connect those two together to provide the service framework. So there are a number of challenges when doing this to build such a system that supports a single service. But we've added a capability called uniform clusters to support this, which we'll now discuss. So a uniform cluster is a special type of MQ cluster, and an MQ cluster is an existing capability that's been available for many years that allow you to build a group of queue managers together with improved connectivity between them and workload balancing for applications. In the uniform cluster, though, each queue manager is essentially equivalent to all of the other queue managers. It's a pattern whereby they are all essentially identical queue managers in terms of the queues they make available and the applications they support. This means that it's readily achievable for applications to move between those queue managers without having any apparent difference to the resources that are available to them. But in this uniform cluster, applications can be dynamically moved between the instances of the queue managers that are available to support the scale and balancing requirements of the application workload. And these uniform clusters are built on top of existing MQ capabilities that enable applications to automatically reconnect to queue managers should the connections be broken, and support applications connecting to one of a group of queue managers using abstracted connection information in a client channel definition table, or CCDT for short. So if we look at this in a bit more detail, we can see in this example, we have 3 queue managers supporting a number of applications, and those applications can be configured to connect to one of those queue managers based on some workload rules or at random. But in this example, you can see that you do not necessarily always get an even distribution of applications across the available queue managers, which might mean that certain queue managers become overloaded by the applications that are connected to them, and the workload isn't performant as it might be. So it's not, ideally, we'd want the applications to be evenly spread across the available queue managers for optimum processing. So one of the features in a uniform cluster is that the queue managers within the group exchange information about the applications that are connected to them, and then they can use that information to initiate reconnects for those applications to rebalance them for optimal distribution. So in this pattern, a queue manager can actually request the application, or more specifically the MQ client that the application uses, disconnect and then reconnect to one of the other queue managers to even out the distribution of those connections. The important thing here is that using the MQ client auto reconnect feature, the applications themselves do not need to be aware of these applications, of these reconnections occurring. It can be transparent to those application workloads. The queue managers continuously assess the distribution of those applications so that when queue managers stop, start, or new queue managers are added to the cluster, the applications are automatically rebalanced to achieve the optimum distribution. This actually is a challenge that many customers have had themselves over the years, and so this is an important capability that simplifies that distribution challenge for them. For example, when a queue manager is taken down for maintenance, nothing would otherwise cause those applications to reconnect back to it once it was available, whereas with the uniform cluster capability, that happens automatically. We continue to extend the uniform cluster capabilities, so if there are any features that you would like us to consider for that, please let us know. Other availability features that we've been doing are around connectivity for Liberty, and specifically for transactions with Liberty. So Liberty uses an XA protocol to connect to resource managers such as MQ, and this means that you've had challenges providing connectivity for a Liberty server if you want it to be able to connect to one of a number of queue managers. This is because in the past you would have had difficulty for Liberty resolving transactions in a safe way if it connected to a different queue manager that was unaware of the transactions that were in flight when connections were lost. On ZOS, we've had a capability called group units of recovery since MQ 701, which have alleviated this problem by having a queue sharing group acting as a single logical queue manager for Liberty to use. But prior to now, we've not had such an equivalent feature on distributed platforms. In 9.1.2, in conjunction with Liberty 18, we've actually got a feature whereby Liberty can now exploit queue manager CCDTs to allow it to connect to multiple queue managers in a group. In this environment, if Liberty has an in-doubt transaction and it loses connectivity to one of the queue managers, it can reconnect to different queue managers in the group and continue processing, and it will remember that in-doubt transaction until it reconnects back to the original queue manager, where it can then be safely resolved. This avoids the risk of those transactions being inadvertently assumed to have completed when they're in doubt on a different queue manager that Liberty is no longer connected to. So this actually provides the improved availability for Liberty to connect to the queuing systems by having a pool of queue managers that it can connect to for availability, whilst maintaining that transactional integrity that's important. Okay, so if we now look at how we can enhancements we've made to help you expand your MQ network. So by this, we're looking at different deployment patterns that you might have and how you might connect systems together. So we have increasingly seen MQ systems connected across large distances in different data centers around the world for availability. Maybe you built up different availability zones for your applications. But the longer distances that you have to transmit data over, the more likely you are to encounter network latency challenges around the speed that data can be transmitted between those locations. One of the products in the IBM integration suite is called Aspara, and which is geared up for transmitting large amounts of data over large distances in a highly performant way. MQ Advanced can now exploit the FASP IO gateway, which is the protocol that Aspara uses to allow data to be transmitted over long distances between queue managers. In this example, you can have a FASP gateway in front of each queue manager within your network, and then you use standard TCP/IP connectivity between your queue managers to the gateways, and then the FASP protocol, which is more performant than standard TCP/IP, can then be used to connect those applications together, those queue managers together, by having improved channel performance for the network data they're transmitting. In this particular example, we can see some of the significant performance gains that you can get increasingly as network performance and latency rises over the distance that you're transmitting the data for. So here we can see that the messages per second that you can achieve in the green bars are significantly higher than what you would achieve using a standard TCP connection that's shown in the red bars on the left. So this really allows you to have improved performance for sending data over larger distances between queue managers. Similarly, as we see multi-cloud deployments and data being connected between data centers over larger distances, you also find that those locations have different firewall rules surrounding them to protect the data that's within them and the applications that are running there. So in this kind of hybrid multi-cloud environment, you typically want to have kind of like boundaries between those locations for integrity and security. So one of the features that MQ has had as a support back for many years is something called Internet Pass-Through. Internet Pass-Through allows you to implement a proxy layer for your MQ traffic so that you can actually tunnel your connectivity over public internet in a secure way between your queue managers hosted in your different environments. In 9.1.4, we've actually pulled that support back into the base product. So Internet Pass-Through is now part of the standard MQ offering. So you can actually exploit this now as a fully supported feature of MQ to allow you to provide this connectivity between systems over public connectivity. Gwydion Tudor, one of my colleagues, has a dedicated session to discuss Internet Pass-Through in more detail, which is session 2BE. So if this is something that is interesting to you, then I would recommend that session to you. So if we now look at how we can manage MQ and some of the features that we've been doing to improve this experience for you. So I mentioned that increasingly systems are being configured in a way that supports automatic deployments to improve the efficiency of those deployments and so forth. So scripting, although it has been important in the past, is increasingly important to allow those configurations to be deployed. So MQ has evolved a number of features to support this. The first thing is that you can run your MQSC commands remotely using Run MQSC as a client application. This has been available for a while now, but not everyone seems to be aware of it. So we're just mentioning it now that you do not have to use the Run MQSC command locally on the same system to the queue manager you're connecting to. You can use Run MQSC as a remote client from any system that you need to run it from. We've also been making some enhancements to some of the MQSC commands to make them more idempotent. By that, we mean that you can run the command multiple times in kind of quick succession, and the result is the same as if you run that command just once. This means it's much easier for you to repeatedly run the same scripts to get to a known state rather than having to delete objects before you can redefine them again or so forth. So we've had the replace option on commands such as define queue, define channel for a while, but some of the commands such as start channel were a little bit harder to achieve idempotency for, because if the channel was started, then you couldn't start it a second time. But we've improved that now with some of the command options, so you can actually exploit that to get more repeatable scripts that you can run in your environments. We've also enhanced the queue managers on distributed platforms so that they can actually read some MQSC scripts when they start, similar to how you can exploit the CSQ imp2 DD statement on ZOS queue managers to define objects when the queue manager starts. This means it's much easier for you to push out some definitions to queue managers, especially if you're spinning up new containers and have those definitions automatically deployed for you. You can have similar features for the queue manager ini files, which define settings that it uses for how it works. And finally, we've built a REST API over a number of years now to allow you to actually define your object definitions remotely over a RESTful interface rather than needing to use the standard MQSC facilities from MQ clients. So if we look at REST in a little bit more detail, we started off providing some bespoke REST APIs for certain types of objects, but then we decided to change our approach and just support MQSC statements in general. Initially, the MQSC REST API took the command as a single string, similar to how you would type it into on MQSC. And then you would then get the output as a single string that you'd have to parse. In 9.1.3 and now rolled into the latest 9.2 long-term support release, we have an improved syntax for how you can do this, which is exploits JSON in its entirety to allow you to have a more structured and readable format for your data. So now you can actually define an MQSC command using a number of JSON attributes in a JSON object, and then you can actually receive the data back from that command as a similarly parsed structure that you can access, which makes it much easier for you to implement these commands in scripts and then process the data that's sent back. At the same time, in 9.15 and thus also in 9.2, we deprecated some of, or stabilized some of the original URLs that we added, because we see this as this new approach as much more the way we want to go in the future. So there's also another session that discussed MQ REST APIs in the GSC conference this year. That's session 6AJ. So if you want to know more about the REST interfaces that we've implemented in more detail, that's a good session for you to go to. I mentioned before about the fact that it's increasingly common that you want to be able to run some of these definitions when you're provisioning new queue managers, particularly tutored in containers. This is kind of similar to the kind of code as config. So that was for the queue managers. To support that similar capability for applications, we now allow you to define your CCDTs as JSON rather than relying on a binary file that was generated by MQ that you had to distribute between your applications. So you can now define the channel connection information for your applications in a JSON structure, and then those applications can then read that data at runtime to determine where they can connect to. This means it's much easier for you to define these definitions as code that you build as part of your application or you distribute with your applications that you can then embed in your own kind of automation pipelines if you need to. Another benefit of this is that the JSON format CCDT supports multiple channels of the same name, so you don't need to have different channel names for different queue managers that you want the application to connect to, which makes it particularly suited for uniform clusters where you want each queue manager to have a similar set of object definitions to it, and then you can have the connection information for all of those queue managers in a single CCDT that the applications can exploit. You can then have the applications connect using to any one of the queue managers at kind of at random, or it can be used to allow it to connect to one of the specific queue managers as directed by the uniform cluster rebalancing logic. If we look at some of the queue size control enhancements we've made now, on ZOS, we've had storage classes for many years that allow you to essentially implement quotas for your application messages. On distributed, the features available to date have previously been just the maximum queue depth and the maximum message size, which work well when your message sizes are consistent. But when application workloads have highly variable message sizes, it makes it very hard to effectively implement quotas for the applications to prevent them consuming all the available backing storage that might otherwise impact other applications using the same services. In 9.15, and we actually added an ability on distributed platforms to specify the maximum size of each individual queue on disk, so that you can effectively implement those quotas yourself, similar to how you might do on ZOS with storage classes. At the same time, we also allowed the maximum size for any given queue to be increased, so you can now have a distributed queue manager supporting queue sizes of up to 2 terabytes that provides you the ability to have a much larger buffer in response to an extended outage, so you can continue to store application messages until the service is restored. The MQ Web Console is a feature that provides a web management interface for MQ, so you can point your browser at a Liberty server that is hosting some applications for MQ, and by those applications then interact with the MQ queue managers to allow you to manage your systems. those applications are provided by the MQ offering. So here you can have a web browser managing your queue managers, so you can connect to it, you can define your objects, you can understand the depth of those queues and so forth, all the sorts of similar concepts that you would have done before using perhaps either MQSC or MQ Explorer. It doesn't contain the full set of features of Explorer, but we're continuing to evolve what's available in the console. In 9.2, we've updated it to have a different look and feel. This is because within IBM, we're trying to ensure that all of the different products have a consistent user experience now, which is particularly important as we see offerings such as the Cloud Packs be continually involved, where you want to have a consistent user experience for all of those products and features as they work together. So in 9.2, we've updated the console to support this. One of the challenges that we've had for customer for many years is managing Cipherspecs for TLS channels, whereby each of the Cipherspec you used had to be defined consistently and explicitly at both ends of the channel. This made it very difficult to allow you to update the Cipherspec that you wanted to use, particularly in large environments such as large clusters of queue managers. We've actually now added support for Cipherspec Aliases that allow you to configure your queue managers and your channels to use TLS at a particular version or higher, which gives you greater flexibility so that you can roll out changes gradually through your MQ infrastructure rather than having to make the same change simultaneously at both ends of channels. This makes it much more consistent with how TLS works within the industry, and it avoids some of those maintenance challenges you'd have when you need to use a different Cipherspec in response to kind of vulnerabilities that might be found in ones that you're previously using. At the same time, MQ is rolling out support for TLS 1.3 across the platforms and languages and protocols that we use, so you can actually take advantage of the latest industry standard for TLS. MQ on ZOS can now support data encryption that was added in ZOS 2.2. So you can actually exploit the data encryption facilities of the platform for all of your MQ datasets. Initially, it was supported only for your archive logs and things like that. But from 9.1.5, you can actually now use dataset encryption for your active logs as well. So you can use that capability for your entirety of your MQ storage on the mainframe. This provides obviously increased security for that data and exploits the features of the platform. However, AMS, which is MQ's advanced message security capability, builds upon data at rest protection by providing end-to-end encryption for messages as they flow through the MQ network. This means that data can be encrypted by an application, and it is encrypted through its entire journey through MQ until it's finally processed at the other end by the target application. This means that AMS then provides added protection to just data at rest, because MQ administrators can't access the data by browsing queues at any point. So if we look at this and how it's been implemented in the past and continues to be implemented today, applications encrypt the data or digitally sign the data at the point that that data is put to the first queue manager. It remains encrypted and signed as it passes through different queue managers in your topology, and then it is only verified or decrypted by the target application. On the distributed platforms, we allowed that encryption or signing to be performed at the first queue manager rather than by the application before it's sent, to support application environments where it was difficult to distribute the certificates to all the different application instances, or where the application client environment didn't support the AMS capability. So that's been valuable on the distributed platforms. But on ZOS in 9.1.3, we've added the ability to perform that encryption or decryption or signing at queue manager boundaries. This is particularly useful when you want to send data to a third-party business partner or other organization, whereby you might have a policy for that all messages must be encrypted on your queue managers, but your business partner might not have that requirement. Therefore, you can actually have messages automatically encrypted or decrypted at the organizational boundary as they pass between queue managers, which is an important feature that many customers had asked for. So we've discussed more about protecting messages with encryption in session 6 AM tomorrow. So that's a good session to come to if you want to understand more about advanced message security. Managed file transfer is a feature of MQ that allows you to exploit the MQ connectivity for transferring files between locations, or transferring files and have them generate messages that can then be put on queues based on records in those files. MFT supports active standby models for how the agents that support the file transfer. And we've also continued to extend the REST APIs that allow you to monitor and configure your file transfer agents within the MQ network for added automation benefits and ongoing monitoring integration. So we've got a 10 minutes left, so we can have some look at some of the developer enhancements we've made. Firstly, we have a new site for developers to go to where they can access tutorials and useful resources to help them build applications, including a developer badge that you can achieve to have a digital credential to say that you've got a basic understanding of MQ and how to build applications. But the tutorials are really useful for new starters and learning how to take particular concepts and deploy them in the real world. And we're always looking for new tutorials and building new content in this center. On top of that, we've also increasingly made samples available online rather than having them just shipped with the product. So you can actually take those samples and use them to build your own applications using the resources available online. Some customers and some people have a perception that MQ is all about very large systems. You can actually demonstrate the simplicity of MQ using some really simple use cases. So there's a system called Scratch, which is a kind of graphical way of demonstrating how messaging works, which you can use to explain concepts to people that maybe aren't familiar with how MQ works. And you can also actually host a queue manager on a Raspberry Pi, which demonstrates how lightweight a queue manager actually is. So it's really easy to build simple systems using the Raspberry Pi offering, which is available, and more information is available at that link shown at the bottom of the slide. In terms of actually helping you build applications in the business environment, we're increasingly looking at what we can do to simplify the experience for application developers. You can now obtain the MQ Java classes and JMS classes directly from the Maven repository, which is a common location for sourcing Java resources for developing applications. And similarly, you can get the .NET client resources from the NuGet repository. We also now have a redistributable MQ client, which you can then use to take the MQ client and build it into your own applications without needing to source and install MQ separately. That redistributable client now also has the MQ SDK built into it, so you can use it to actually obtain the header definitions that you need to build your own applications at the same time. Similarly, there's an MQ Advanced for Developers offering, which you can download and use for free to help you develop your MQ applications, and that is available on Windows and Linux. And we now also have a macOS MQ client and SDK for developers that they can use in their own environments. We also continue to look and expand in the languages and environments that are supported for applications. I mentioned you can use the REST API for administration of your queue managers. There's also the ability to exploit REST for your messaging operations too, if you don't need the full qualities of service that the MQ client provides. You can therefore then expose RESTful APIs to allow applications to put, get, browse, and publish messages in your MQ network using a really simple RESTful interfaces that can be exploited from all different types of applications. We also support a lot more language bindings. So we've made examples available for how you can use Node.js and Golang, both using MQI interface and JMS. We've added support for AMQP and Cupid JMS applications in recent years. And at the same time, we've also got support for .NET Core, which is available both on Windows and Linux. So that's a very quick overview, if you like, of all the different enhancements we made. There's not time to cover everything, so here's another quick recap that you can look at. So we continue to make large numbers of enhancements to the MQ product in response to customer requirements and market needs. So please keep checking on what we're doing and provide us feedback if you would like us to do enhancements that you've not seen. So that was all I had in the session today. So we've got 5 minutes left. So are there any questions, Mel?
There are no questions at the moment.
Okay. We've got a few minutes if someone wants to ask a question. So by the way, these slides are available to download from the GSC agenda. So if you want to take these slides and look at them in your own time, they are available there now for you to access.
Right. Thank you very much, Jamie.
Okay, all right. So please submit your session feedback as per usual. There's the URL. Always grateful for any feedback you have, so we can improve content in the future. And also, GSC UK conference have their charity this year. So there's the information about it. That's attached to all of the sessions this week and next week.
And both the the charity link can be obtained from your BYOA screen, as well as the feedback form. The next MQ session is at 3 o'clock GMT on REST APIs in MQ. So I hope to see you there. Thank you very much, and thank you, Jamie.
Okay, you're welcome. Have a good day.